Hello friends, welcome back to this channel. Today we'll start with the first chapter of Standard 12 Mathematics, and the name of the chapter is Relations and Functions. You had already learned about the basics of relations and functions in Standard 11, about the relations, domain, codomain, range, and so on. Yeah, so now today we are going to start with types of relations. Okay, so let's start. Types of relations: empty relation and universal relation. Now see, if I take a relation on set R, if I take a relation on set R, let's say set A, then R will be subset of E cross A, right? Now, if I take any relation such that it is equal to phi, then obviously this is subset of A cross A, right? Then that relation is called empty relation. Clear? Now, universal relation. See, there are two extremities. There are two extremities. One is phi and another is A cross A. Phi, that is null set, this relation is called empty relation, and A cross A, that is called universal relation. Okay, so A cross A, that will be universal relation. Here, let's take example. If I take set A equal to 1, 2. Clear? Now, if R is defined as A, B such that A minus B is greater than phi, A, B belongs to A. Yes. Now see, A, B, the value of A and B both belongs to A. Means I can take either 1 minus 1, 1 minus 2, or 2 minus 2, or 2 minus 1. But in every case, A minus B can never be greater than 5. So the relation R will be an empty set. Clear? Okay. But now if the relation is like this, A B such that A minus B is an integer and AB belongs to A, right? Clear? So now see, I can take value of A, that is 1 and 2, and value of B, that is 1 and 2, and we know that when two integers are subtracted, the answer will be always integer. So what will be this? 1 1, 1 minus 1 0, integer. 1 2, 1 minus 2, minus 1, integer. 2 2, 2 minus 2 0, integer. 2 1, 2 minus 1 1, that is integer, right? So now see, this is what? This is nothing but this is A cross A. That means this is universal relation. A universal, that will be relation. Empty relation. Okay, so these are the examples of empty relation and universal relation. Okay, now let's move to the next type of relations. The next is reflexive, symmetric, and transitive. Okay, so first let's start with the reflexive. Okay, what is reflexive relation? Now see, if the relation is on set R, if the relation is on set A, then for every, this is the symbol for every element A belonging to A, A must belongs to R. For every element A belongs to A. If AA belongs to R, then it is reflexive. Okay, then it is reflexive. Remember, every element means if the set A is such that 1, 2, 3, right? Then the relation must include the ordered pair 1, 1, 2, 2, 3, 3. Then this relation can be said to be a reflexive relation. Clear? So if it includes 1, 2, then it's okay. But 1, 1, 2, 2, and 3, 3 must belongs to R. Means this must be included in R. See, then this is reflexive. See, if the relation is like this, 1, 1, and 2, 2, 2, 3. Let's stop it. Now see, this relation does not have 3, 3. That means it is not a reflex. Clear? So to prove whether a relation is reflexive or not, you have to prove that for every element A belonging to A, right? Ordered pair AA belongs to R, then only it is reflex. Clear? Now, if you want to prove that it is not reflexive, means opposite, right? The question can be asked that verify that the given relation is reflexive or not. That means you can do two things. First, either prove that it is a reflexive, means every element A for every element A ordered pair A belongs to R, or else just find out that for any element there exists A. I am talking about not reflexive. Okay, so for that, for any, this is a symbol for there exists any element A belonging to A such that A does not belongs to R. Then it is not reflexive. Right? So in this case, I can say that 3, 3 does not belongs to R. Means see, 3 belongs to A, but 3, 3 does not belongs to R. Therefore, it is not reflex. Okay, so if the question is asked that whether it is a reflexive or not, you can select any one of the matter. Either prove that for every element AA belongs to R, or else just find out any single element such that AA does not belongs to R, therefore it is not reflexive. Clear? Now this symbol, one more thing I want to write down. This symbol like AA belongs to R. This can be also written in this way. E R A. That means AA belongs to R. Clear? If I am writing like A R B, then this means that AB belongs to R. So this is the short form. If you don't want to write down complete this, you can write down in this way. Clear? So this was about reflex. Just note down about reflexive relation, then we'll move for symmetric. Okay, now let's move to the next type, that is symmetric relation. Symmetric. Next is symmetric relation. Now see here for every or for any element, let's say A and B belongs to A. Okay, now the relation is on set A. So if A, B belongs to the relation R, then that must imply that B, A also belongs to R. Then it is symmetric. Okay, so remember if AB belongs to R, then implies BA belongs to R. Clear? So see if there is a set A, 1, 2, 3. Then the relation I can write it down 1 2 2 1 1 3 comma 3. See if this is the relation, that means this is symmetric relation because see 1 2 belongs to R, that means 2 1 also belongs to R. This implies that 1 3 belongs to R, 3 1 also belongs to R. See there is a difference between reflexive. In reflexive we are writing for every A belonging to A. Here it is not for every AB, right? See in this example I have taken 2 3 and 3 2, right? If this belongs to R, then also reflexive. But see here in this example 2 3 does not belongs to R, right? So it doesn't matter whether 3 2 belongs to R or not. Clear? But if 2 3 belongs to R, then that must imply 3 2 belongs to R. So, right? In reflexive, we were taking every element, right? So here the condition is if AB belongs to R, then only it must imply BA belongs to R, right? So this is about symmetric. Okay, if AB belongs to R, that must imply BA belongs to R. Then only it is symmetric. Okay. So now if you want to prove that it is not a symmetric, right? If you want to prove that a relation is not a symmetric, you can do two things. When the question is asked, show that whether they are symmetric or not, then either prove it is symmetric or not symmetric. This is the other way to do it. That for AB belongs to R, if that implies BA does not, sorry, AB belongs to R, but BA does not belongs to R. In other sign, I can write it down like this: ARB. That means AB belongs to R. Right? This you can write down in this way. But see here, BA does not belongs to R. That means it is not symmetric. Right? So if the relation is like this way, 1 2 2 1 1 3 3 2 3, right? So now here we can say that 2 3 belongs to R, but 3 2 does not belongs to R. Therefore, it is not symmetric. Clear? So this is the other way. Either prove it is a symmetric using this way, or just find out any one ordered pair that belongs to R and the reverse ordered pair does not belongs to R. So it will not be a symmetric. Clear? So just note it down about symmetric relation. Now let's move to the next one, that is transitive. Transitive. Okay. Now again we will say the relation is on set any set A. Now for any element A, B, C belonging to A, right? See, the relation is on set A, right? If AB belongs to R, BC belongs to R. See, the second element of the first order pair and the first element of the second order pair, I am taking same. If this is the condition, then A, this implies that, this must imply that AC belongs to R, right? Other way, I can also write it down like this. If A R B, B R C, then that must implies A R C. This is the symbol. AB belongs to R, right? So if this is the case, then the function, then the relation is transitive. Okay, I'm taking example again. If set A is 1, 2, 3, right? Let's say also number 4. If the relation is like this, 1, 2, 2, 3. Now see, this is matching the second element and the first element. So 1, 3. If this is the case, then this is transitive. Again, see, it is not for all. If the first condition, if this condition, if this is there, then AC must belongs to R. Clear? So there is nothing about 4 because it is we are not taking any element here. Clear? Now, if you want to prove it as a not transitive, right? If you want to prove the relation is not transitive, right? Then you have to show that AB belongs to R and BC belongs to R. But AC does not belongs to R. In that case, the relation is said to be not a transitive relation. Okay, so if the relation is was like this, 1, 2, 2, 3, 1, 4. Now see here, in this case, you can see that 1, 2 belongs to R, 2, 3 belongs to R. But 1 and 3, because this is same, 1 and 3 does not belongs to R, therefore it is not transitive. Clear? Okay, so this was about transitive. Yeah, so either prove that it is transitive using this or prove that it is not transitive. Okay, if you are not able to find any such pair like this, then it will be transitive. Yeah, so that was about transitive relations. Just note it down. Now let's move to the next one, equivalence relation. Now see, when can we say a relation as an equivalence? If it is symmetric, if it is reflexive, if the relation is symmetric, and if the relation is transitive, then that relation we will call it as equivalence relation. So see, what type of question can we ask? show or prove that the following relation is an equivalence relation. So what you have to do in that? First prove that the relation is reflexive, then symmetric, and then transitive, right? And so if all the three will be there, then it will be an equivalence relation. See, in MCQ there are different options, like a relation is given and then option A, it is reflexive but not symmetric and transitive. It is symmetric and reflexive but not transitive. It is transitive and symmetric but not reflexive. And fourth option, it is an equivalence relation, right? So see, if any one of these three, if any one of these three is not true, then also the relation will not be equivalent. Means if it is symmetric, if it is transitive but not reflexive, then also it will not be an equivalence relation. Okay, so I hope you got it about the type of relationship. When will you say it as a reflexive? When will you say it as a symmetric? When will you say it as a transitive? And when will you say a relation as an equivalence relation? Clear? So now let's take some examples. Okay, let's start with exercise 2.1. Sorry, 1.1. Exercise 1.1 of NCERT textbook. Okay. Question number 1. Determine whether each of the following relations are reflexive, symmetry, and transitive. Okay. Let's take the first one. Okay. It is given that A is equal to 1, 2, 3 up to 14. Okay. And the relation R is equal to xy such that 3x minus y equal to 0. Now see here, if it is a reflexive, then 1 1, 2 2, 3 3, 4 4, it must belongs to it, right? See here, this is the relation 3x minus y, that means 3x is equal to y. So now if I take 1 1, yeah, sorry, it's 3x, not 3y, right? I cannot write down that 3 into 1 equal to 1. No, right? So that means this does not belongs to R. Therefore, it is not reflexive. Okay? Clear? Here is this. Now, for the second one, that is symmetric. In symmetric, it is that AB belongs to R. That means BA belongs to R. Now, see, if I take Y1, okay, here X, sorry, if I take X1, Y will be 3. So I can write it down that 3, sorry, not 3, 1, 3. X is 1, then Y equal to 3 into 1, 3. 1, 3 belongs to R. Here, but do 3 1 belongs to R? Can I write down x as 3 into 3 equal to 1? No, right? So that implies 3 1 does not belongs to R, right? Therefore, it is not symmetric. Okay, clear? So it is not a reflexive, not a symmetric. Now, for the third case, transitive. Let's take 1 3 belongs to R. When I take x equal to 3, right? So 3 into 3 9, y will be equal to 9. 3 and 9 will also belongs to R because we are having the element 3 and 9 both, right? Okay, but can I write it down 3 into 1? Let me check. If 1 9 belongs to R, then it will be transitive. If not, then not. So 1 9, 3 into 1 equal to 9. Is it correct? No. Therefore, this does not belongs to R, right? See, 1 3 belongs to R, 3 9 belongs to R, but 1 9 does not belong to R. Therefore, it is not transitive. right? So question number one, the relation is not reflexive, not a symmetric, or also not transitive. Clear? Just note it down. Now let's move to the second one. Question second of first, the relation is given r equal to xy such that y equal to x plus 5 and x is less than 4. And see, the relation is in set n, so natural numbers. Okay, so see, let's see first about the reflexive, right? If I take 1 1, see, there are two options. Either prove that for every a belongs to r, okay, then it will be reflexive. And if you want to prove not reflexive, then just select any one ordered pair, 1 1 or 2 2, any such like that, which is not belonging to r. So I will select the second one. Here y is equal to x plus 5, right? So first, for 1 1, if I take 1 1, right, then can I write it down 1 equal to 1 plus 5? No. So I cannot write it down. Therefore, 1 1 does not belongs to R, and that means it's not reflex. Okay. Now let's see for the second one. Okay. For symmetric, I should select first any ordered pair that belongs. So let's take x as 1. Okay, then if I take x as 1, then 1 plus 5, that will be equal to 6, right? So 1 6 belongs to R, right? But what about 6 1? Can I write down 6? Sorry, y is 1, that means 1 equal to 6 plus 5? No, I cannot write it down. Clear? Therefore, it is not symmetric. Here, now let's see for the third one, that is transitive. Now let's see, take 1 6 belongs to R. Here, now if I take x equal to 6, then it will be 6 plus 5, 11. Right? 6 plus 5, 11. So I will write down 6, 11 belongs to R. Okay, here 6, here 6. So if it is transitive, then 111 must belong to R. Let us check. Can I write down 11 is equal to 1 plus 5? No, that is not equal to 5. Therefore, this does not belongs to R. Therefore, it is not transitive also. Okay, it is neither reflexive nor symmetric, and also it is not a transitive relation. Clear? So note down the second question. Let's move to the third one. Question number third is set A is given 1, 2, 3, 4, 5, 6, and the relation is on set A, and it is such that xy is such that y is divisible by x. Okay, so now let's take for any element A belonging to A. Every number is always divisible by itself, means A is divisible by A, right? So what does that mean? A A belongs to A. Here 1 1 2 2 3 3 4 4 5 5 6 6 will belong to A because the number will itself divisible by the number will be divisible by itself. Therefore, it is reflexive. Okay, now for the next one, that is let's select any two number which is and in a ordered pair which is belonging to R. Clear? Let's say 4 2 belongs to, sorry, see, I can say that 4 is divisible by 2, right? So 2 4, y is divisible by x, 4 is divisible by 2, that belongs to A. Clear? But can I say that 2 is divisible by 4? No. 4 is divisible by 2, but 2 is not divisible by 4. Right? So 2 4 does, sorry, not 2 4, 4 2. 4 2 does not belongs to E. Right? Because 2 is not divisible by 4. So that means it is not symmetric. Clear? See, when you are going to prove not, then you can take example. Okay, and when you have to prove it, then don't take example. Okay, now see here for the reflexive. Now see, if I take, let's say, for A, B belonging to A, let A, B, and C. A, B belongs to R and B, C belongs to R. Clear? So what does this mean? B is divisible by A. And here, okay, I need to change. Okay, and BC belongs to R, that means C is divisible by B. Now see, B is divisible by A, right? And C is divisible by B, right? Or else C is divisible by B, which is divisible by A. Let's take example. Like 125 is divisible by 25 and 25 is divisible by 5. That means 125 divisible by 5, right? So what does this imply? This implies that C is divisible by A. So this shows that C belongs, so to, sorry, this will be small a, not capital A. This shows AC belongs to R. So what does this mean? This means that it is transitive. Okay, so this is reflexive, yes. Symmetry, no. Transitive, yes. So this given relation is reflexive and transitive, but not symmetric. Yeah, just note it down. Okay, now let's move to the next one. That is question number 4. Question number 4 of first is the relation is on set Z, means all the integers. Now R is x, y such that x minus y is an integer, right? So for any element A belonging to Z, A minus A will be equal to 0 and that belongs to Z, right? Means that is integer. Clear? Okay. So what I can write down, A belongs to R, that implies it is reflexive. Clear? Now let's take for transitive, sorry, symmetry. Now let A B belongs to R. So what does that imply? A minus B is an integer, right? So this means that B minus A will be also an integer. Okay, it just will be sign, change the sign. If a minus b is positive, then b minus a will be negative. But both will be an integer, right? So this is also an integer. B minus a is an integer. That means BA belongs to R. See, AB belongs to R. Prove that BA belongs to R. Therefore, it is symmetric. Okay. Now for third, let AB belongs to R and BC belongs to R. So what does this mean? A minus B integer, B minus C integer. Clear? Now just add these two. Well, now we know that when we will add to integer, the answer will be integer. So a minus b plus b. B gets cancelled minus c. So this implies a minus c is integer. So that means AC belongs to R. That implies it is transitive. Clear? So the given function, the given relation is reflexive, symmetry, and transitive. Therefore, it is an equivalence relation. It is not asked, but we can write it down. Therefore, it is an equivalence relation. Clear? So note it down. Now let's move to the next one. The fifth one of question number one are the general examples. So I will solve just one of them. Rest you have to solve by yourself. A, here A, it is given that x, y said that x and y work at the same place. Now, if I take x and x, both will be always working at the same place, right? Means actually it is only one individual, not two different individuals. So if x is working in one company, then x will be working in the same company because he is the same. So x and x works at the same place, therefore it is reflexive, right? Now x and y walk at the same place, that means xy belongs to R. Then y and x also walk at the same place, right? It's just the reverse, so it is also symmetric, right? The third one, x and y work at the same place, y and z work at the same place, so obviously this will imply that x and z also work at the same place. So this belongs to R, this belongs to R, this is also belonging to R, so this is also a transitive, hence it is an equivalence relation. Yeah, so like this you solve the B, C, D and E also. Clear? Okay students, so that's it for today. In our next video we'll continue with exercise 1.1. Thank you.